Okay, welcome. This is Mr. Wilczewski's lessons on stoichiometry, and this is section 2. We're going to talk about patterns and discovering those patterns and applying those patterns to solve problems. So rather than memorizing, how to do a particular problem, if you see the patterns that apply, you'll be able to solve more problems with the same strategies. Okay, so all of the problems that we are going to give you in this session start with a known stuff, a known material. Maybe it's the number of molecules or ions. We'll call them particles for short until we know what they are. Or we're giving you the mass, so many grams of a chemical. Or if it's a gas at STP or given conditions, we could even give you a volume of that gas. Or we could even give you a quantity of energy. And then when I ask you to convert that known material into a quantity of material that you're looking for, that you're trying to find. So we could ask you to find the number of molecules, ions, particles, atoms. We could ask you to find the mass, or we could ask you to find the volume if it's a gas. Notice the volume only works for gases. All right, you need to know temperature and pressure conditions, usually STP. And energy, we could ask you to find the energy. Well, the key here to go from the known to the find is to convert into moles. Now, if you have the number of particles and you can convert that to moles of that same chemical, then you can find the particles of any other chemical. Keep in mind, stoichiometry is working with balanced chemical equations from a chemical reaction. Or you could find the mass of one of the other chemicals, or the volume if it's a gas, or even the energy if you're given a thermal-chemical equation. All right, same thing if you're given the mass of your known chemical, you can convert it to any one of those other things: particle, mass, volume, energy. If you're given the gas volume, same thing. If you're given the energy, same thing. All right, so you can make all these different conversions. So from the known, convert to moles. You can figure out any of those variables, quantities of what you're trying to find. Now, to convert to moles, once you convert a chemical into the moles of itself, of the same chemical, you need to apply the mole ratio. You have to convert the moles of the known chemical to moles of the chemical you want to find. And that's why in previous versions of this stoichiometry lesson, we emphasize the mole ratio. Because you take the moles of the known, and we're going to show you how to do each one of these steps in a little bit. So this is the overview. Once you have one of these things, you convert it to moles of the known. Then you use this mole over mole ratio with the moles of the find in the chemical you're trying to find in the numerator and the moles of the known in the denominator. Then the moles of the known will cancel, and you get moles of the chemical that you want to find. And then there's another step which will show you how to convert those moles either to particles, to mass, to gas volume, or energy of the other chemical. So notice on the left side, you're starting with a known quantity of a certain chemical. In the middle, you convert that chemical using the mole ratio from the balanced chemical equation to the moles of a second chemical. And then you have a final step to convert those moles of that chemical into one of these or all of these different quantities. Okay, so we're going to call this a roadmap, a stoichiometric roadmap. And you could start with the particles of the known. That could be one of the places you start your journey. Or you could start with the mass of the known, or the volume of the known in liters, or the energy in kilojoules. And then you're going to convert that to the moles of the known. And we're going to show you each one of these processes. And then you convert the moles of the known to the moles of the find. And then you can convert the moles of the find to particles, or mass, or volume, or even energy. So what you're building here is a pattern or a roadmap to how to solve all these different types of stoichiometric problems. So if you were in a in-person class, I would probably assign to you a quiz, or maybe even in a virtual class. Just check the syllabus. There might be a quiz where I'm asking you to draw these stoichiometric equations from memory, this whole pattern. And I'm asking you to not to memorize as much as to internalize the pattern. Okay, so particles of the known, to convert that to moles, here's what you would do. You'd multiply it by this conversion factor, 1 mole of the known over Avogadro's number, 6.02 times 10 to the 23rd particles. Then the number of, no, we're calling it particles now, but in a real problem, you'd know they were atoms or ions or so forth. So the particles of the known would cancel, and we'd be left with moles of the known chemical. So here's an actual problem. How many moles in 1.2044 times 10 to the 24th atoms of iron? Now, always start with the ending here. That's why I wrote down moles of iron first. So you have your molecules, they're not molecules, they're atoms of ions. That's a typo. So you'd have so many atoms of iron, and you'd multiply by a conversion factor that have moles of iron over atoms of iron. And how many atoms of iron are there in a mole of iron? Well, Avogadro's number, 6.022 times 10 to the 23rd. Notice those units cancel. Before you do any math, check those units cancel. So the atoms of iron cancel here and here. And now you'd get moles of iron as your answer. All right, and this answer is 2. Now, I kept the math simple here because I want you to see the concepts and not get hung up in the numbers. All right, so that's the first branch of this road. The second branch, well, you may end up starting with the mass of the known chemical. Then you'd multiply by this conversion factor, 1 mole of the known over the molar mass. Now I'm going to ask you now, take a look at this. Do you see a pattern here? Some people can see it already. Most don't yet, but keep looking. Look for the pattern. If you can see the pattern, then you won't really have to be memorizing stuff. You'd be internalizing a pattern. So in this case, the mass of the known chemical in grams would cancel, and then you would end up getting the moles of the known. All right, so let's do an actual problem. So how many moles in 36.04 grams of water? All right, so you're trying to find, always ask yourself the first question, what are you trying to find? Look for the words how many, calculate, find, determine. Here it says how many moles. All right, so you're looking for the moles of water, and your starting data point is your 36.4 grams of water. So you're going to build your conversion factor. You want to cancel the grams of water and turn them into moles. So moles go in the numerator and grams go in the denominator. So now you have to answer that question, how many grams are there in a mole of water? Well, that's the concept called the molar mass we talked about before. You need a periodic table and a calculator. You'd look up hydrogen. Its mass is 1. You'd probably round it to 1.01. You need to double that, so it's 2.02. And then add that to oxygen, which is 16. All right, so if you need help for that, then go back to the units and conversion lessons and look at the molar mass section. All right, so it'd be 18.02 grams. Now, the grams of water go in the top or the bottom. Well, if you set your units up right, it's obvious that it's 18.0 grams. So grams go in the bottom and 1 mole goes in the numerator. Next step, check those units cancel. The grams of water cancel. And now you can do the math. So do it. Do the math. Pause the tape. Come back when you're ready. If you got 2.000 moles of water, you are correct. All right. All right, so let's look at the next branch of this road. So suppose you were given the volume of a gas in liters, and let's just assume it's STP for now. And then you would multiply by the conversion factor. That would be 1 mole of that gas over the molar volume. Now at STP, the molar volume is a known number that I hope you need to know that number. It's 22.4 liters, as long as the conditions are standard, STP. So let's do an actual problem. So convert 44.8 liters of hydrogen gas at STP to moles. So you're looking for moles of hydrogen. All right. And so you've got moles of hydrogen, and you're starting out with 44.8 liters of hydrogen. So your conversion factor would have moles of hydrogen up top and liters of hydrogen in the bottom. So the liters of hydrogen would cancel. And there's where you need the molar volume concept. The molar volume is 22.4 liters per mole. That's a known quantity. So that goes in the denominator. So 1 mole of hydrogen gas at STP has a volume of 22.4 liters. The liters of hydrogen cancel. All right, now do the math. Stop the tape, do the math, come back when you're ready. All right, if you got 2.000 again, you're right. All right, notice I am keeping the math simple because I want you to see the units, concept, cancellation, and the focus on the patterns in the stoichiometric roadmap. All right, energy. Suppose you were given energy in kilojoules and asked how much energy. You were given energy and you were asked, with this amount of energy, how much of the other thing could you make or produce or would you need? Right? So you would multiply by a conversion factor that would have 1 mole. Notice this doesn't have any chemical associated with it because it's in the balanced equation. You'd have 1 mole over so many kilojoules or perhaps kilocalories of energy. All right, so let's take a look at a problem. So we have the standard molar enthalpy, the heat of vaporization for water. That's a given quantity. You can look it up, 40.79 kilojoules per mole. We usually give it to you. And we're asking how many moles of steam are required to release 81.58 kilojoules of energy upon condensation. So here you're looking for the moles of steam, H2O, in a gaseous state. And the energy you're starting with is 81.58 kilojoules. So your conversion factor would have moles of water in the numerator and kilojoules in the denominator. So they gave, look at it, now go back to the problem. They gave you 40.79 kilojoules per mole. The way they gave it to you, they had kilojoules in the numerator and moles in the denominator. You don't want that exactly. You want that kilojoules, but you want to put it in the denominator. Why? Because you're canceling the kilojoules over here. If you left that in the numerator, you'd be multiplying kilojoules by kilojoules. You'd end up with kilojoules squared. That's not what you're looking for. All right, so the 40.79 kilojoules goes in the bottom. That's why you set these units up first. So you set this up so you know you're trying to cancel kilojoules. You know you're trying to get moles. That dictates everything else should fall into place after that, following those units. That's the whole point. Notice those kilojoules cancel. And do the math, pause the tape, do the math, come back when you're ready. All right, again, our answer is 2.000 moles. Notice we're sticking with the correct number of sig figs. If you need help on that, please refer to the sig figs video. All right, so now after you get the moles of the known chemical, you've gone through one of those steps to get to the moles of what you know. Then you convert it to moles of the find, and you use a mole ratio to do that. So the moles of the known times the mole ratio gives you the moles that you want to find. Now remember, the mole ratio is set up using coefficients in the balanced chemical equation. So you look in the balanced equation in front of the chemical you're trying to find, and the coefficient in front of that chemical is the number of moles that you're going to put into mole ratio in the numerator. You do the same thing for the known chemical, but you put that in the denominator. Why? Because you want to cancel the known and turn it into the chemical you're looking for. All right, so that's the middle part. So we're going to put that right in there. So after those first few steps, after the first step, the second step would be multiplied by this mole ratio. So we're building this whole massive equation for you to be able to understand multiple problems. So we're going to just stick that right there in the middle. So here, so we've got our first steps, one of these 4 steps, depending on where you're starting with. And then after that step, you would, if you stopped your math right here, you'd have the moles of the chemical that are known. And then you multiply it by the mole ratio to find the chemicals that you're looking for. Now, on the other side of the equation, let's go to particles first. So once you've got the moles of what you're trying to find, you need to convert those moles to the particles. So your conversion factor would be Avogadro's number in particles over 1 mole of that particular chemical. Now, take a look now again for the pattern. Look at this side. Look at this conversion factor. Look at that conversion factor. See if you can see a pattern. Always look for the patterns. Chemistry is lots of patterns. All right, so let's do an example. So how many molecules, now I use the word molecules loosely here because sodium chloride is not a molecule, but more about that in the bonding chapter. How many molecules in 0.3 moles of sodium chloride? So your, we'll call them formula units. So your number of units of sodium chloride is what you're looking for. And you're going to start out with 0.3 of a mole. And you're going to build your conversion factor where the number of molecules, or let's say particles, of sodium chloride over the number of moles. So that's Avogadro's number of sodium chloride units over 1 mole of sodium chloride. Notice that the moles of sodium chloride cancel. All right, so do the math. Pause the tape, do the math, come back when you're ready. Okay, the answer is 1.81 times 10 to the 23rd units of sodium chloride. Okay, what if we're looking for mass? So let's see. So if you're looking for that part, your next conversion factor would be to take the molar mass in grams over 1 mole of this, the same chemical, the grams of the chemical you're trying to find over the moles of that same chemical. Here's a sample. What is the mass of 3 moles of water? So you're looking for the mass of water in grams. Your starting data point is 3 moles. So your conversion factor has to have grams up top and moles on the bottom. And you hopefully you recognize this is the molar mass of water, the grams of water in a mole of water, and that number is 18.02, which hopefully you could calculate using a periodic table and a calculator. All right, so make sure those units cancel. All right, so stop the tape to do the math. Come back when you're done. All right, 56.04 grams of water. That's your answer. All right, next, what if we're trying to find the volume of a gas? And let's assume STP for this problem. You'd multiply by the molar volume in liters of that gas over 1 mole of that gas. And since we're assuming STP, we know the number is 22.4 liters of a gas over 1 mole of the gas. All right, so an actual problem would be this. What is the volume of 3 moles of oxygen gas at STP? Here you're looking for the liters of oxygen, and your starting data point is 3 moles. So your conversion factor would have liters up top and moles down the bottom of oxygen. And the answer to that is 22.4. There are 22.4 liters in 1 mole of oxygen. So your units cancel, the moles of oxygen cancel. And so stop the tape, do the math, come back when you have an answer. All right, so the answer is 67.2 liters of O2 gas. All right, what about energy? Well, here's a problem. For the energy, we'll just back up just 1 second. Your conversion factor is going to be the number of kilojoules over a mole. Now, take a look at both sides. Here you have moles over kilojoules. Here you have kilojoules over moles. Back up a step. Here you had moles over volume. Here you have volume over moles. Here you have moles over mass, mass over moles. Here you have moles over particles, particles over moles. And hopefully now you see the pattern. All right. Okay, so let's do an example with energy. The molar enthalpy, or the heat of fusion for water, is 6.009 kilojoules per mole. What quantity of energy is released when 2 moles of liquid water freezes? So now we're looking for kilojoules, given 2 moles of water as our starting data. So your conversion factor is going to have the kilojoules up top and the moles down the bottom. Notice this time we're going to use this exactly the way it is, 6.00 kilojoules over 1 mole. So the 6.008 kilojoules goes in the numerator and the 1 mole goes in the denominator. Check your units. Moles of water cancel. Now, stop the tape, do the math, come back when you're done. Okay, the answer is 12.01 kilojoules. Okay, so this here is the master stoichiometric equation. Enables you to solve multitudes of problems. You could go from particles of one chemical to particles of another, or particles of one chemical to mass of another, or particles to volume, or particles to energy. And you go from mass to particles, mass to mass, mass to volume, mass to energy, volume to particle, etc. All these different combinations. You can also do moles. We could ask you to go from particles of one chemical to the moles of another, which should stop right here. And we don't have to start at one of these 4 starting points. You could start in the middle. We could give you moles of a known chemical. Right here would be. And then all you have to do is multiply times a mole ratio to convert it into moles of the other chemical. And then if you're going further, to multiply by one of these conversion factors to get to particles, mass, volume, or energy. Okay, now I called this a roadmap when I started teaching it years ago, and I just taught particles and mass. I didn't teach volume and energy at the same time. And I found out rather quickly that many students do better if they see the big picture of where you're going, so they understand the whole concepts and they can deal with that and see the big pattern much easier. So then later on I added the volume and energy. But when I first did this, a student looked at my equations on the board and said it looks like a bone. I guess it does. Kind of bone has 2 lobes on either end, like a dog milk bone. And then another student said, no, it looks like Flintstone's car. And I didn't quite get that at first, but they went to the board and they drew it and they said, yeah, you've got your 2 parts that you're calling the bone, and there's a wheel, and Fred sits in the middle. And so my students named this affectionately the Flintstone Bone Road. Now, bear in mind, I'm teaching over 20 years, so maybe there's 2,000 students that know what the Flintstone Bone Road is. The rest of the world is not going to know what you're talking about. So in this course, you can use the term Flintstone Bone Road. If you see anybody outside this course using it, they probably had me or one of the teachers I've trained as a mentor. All right. Otherwise, the proper name is the stoichiometric equations. I like Flintstone Bone Road, but use whatever you want. Okay, so this is the pattern that I would ask you to memorize if it's an assigned quiz. Check the syllabus. Not all courses have this as a quiz. Some do, some don't. All right. Okay. This is a fun assignment. There's a link on YouTube. If you follow this link, it'll take you to a video of a comedy routine called Who's on First video. And sometimes I give this as a quiz. And the quiz question is, what does this Who's on First comedy skit have to do with stoichiometry? Think about that. We're not going to do that today, but have fun with that if you want later. All right, so let's talk a little about the different types of problems. If we started with a mole, so I give you the moles of the known chemical and ask you to find moles of another chemical, that would be called a mole-to-mole problem. If I gave you moles and asked you for particles, it'd be a mole to particle. Or I could give you moles and ask for mass, that'd be a mole to mass. Or it could be a mole to volume. Or we could start with particles and go to moles or particles. These are all different classifications of different types of problems you can get from that one pattern that we looked at. And energy is not even in here. So we could even do multitudes of energy calculations. Now, what I'm asking you to do is to internalize these patterns and be able to recognize the type of pattern you would need to solve future problems. All right, and that's what we're going to do in the next lesson, is we're actually going to practice identifying patterns. Before we even get to solving any problems, we're going to practice identifying patterns.